Welcome to the course on two-dimensional signal processing, principles and practices. This week we will do the Z transform, wherein we had look at the 1D Z transform as well as 2D Z transform. In that 1D Z transform, we have not done that in the signal processing overview. So we would like to take this lecture for the one-dimensional Z transform so that it can be extended to the two-dimensional Z transform. And these Z transforms are useful in the filter transfer function representation. So first we take the 1D Z transform. As we know that there are two types, we can say that it is a bilateral and unilateral Z transforms. So considering that x of z as Z transform, that is a bilateral Z transform of a sequence x of n, that's a 1D sequence, then x of z is defined in such a way that is n is varying from minus infinity to plus infinity, the summation x of n is z power minus n. So we can see in the n varying from minus infinity to plus infinity. For the case of unilateral, that n would be restricted to 0 to infinity, whereas n is greater than or equal to 0, the summation is restricted. So in that case, it is going to be a unilateral sequence. So in reality, we have all of the sequences of n greater than or equal to 0. So in that case, the unilateral Z transform would be much useful. So in this case, that Z, what is the Z represent here? So Z is R e power j omega, where it's a complex variable. And we'll see that detail about this Z complex variable, whereas in the case of Fourier transform and the DFT and all, we have seen that x of k, the bin index, and the DTFT, if you remember, x of omega or x of e power j omega. This Z is here R e power j omega, that needs to be noted. It's a complex variable in the Z transform. So the existence of this Z transform is guaranteed only that when this summation, that is x of n z power minus n, the magnitude of it should be less than infinity. It should not exceed that infinity. So it should be a finite value so that this transform exists. Otherwise, this doesn't exist in the case. So what is the relation that if to get the Z in terms of R e power j omega? So if Z is substituted with R e power j omega, then the n equal to minus infinity to plus infinity x of n r e j omega, and this is the Z is just replaced minus n. So in this case, that we can write this as r power minus n e power minus j omega n. So this comes to a point that where we had seen this equation of in terms of this Fourier transform, that is DTFT. If you recall that discrete time Fourier transform in which x of n e power minus j omega n, these terms were present, right? So in this is the DTFT of, but there is DTFT of this sequence, a sequence x of n, where this x of n is multiplied with r power minus n. So we can say this is the x of r e power j omega is the DTFT of the sequence x of n to r power minus n. If r is 1, that is straight away the DTFT. So we can say that the Z transform is a generalized version of the Fourier transform. So this sequence x of n r power minus n, that the DTFT represents x of r e power j omega. So this convergence, actually this magnitude needs to be less than infinity. As we said, this whole sequence z power minus n, where this contribute to the e power j omega n is make only angle. So we have the x of n r power minus n magnitude is less than infinity. So the range of r for which this condition is satisfied. So we need to find the r values for the x of n, given x of n, find the x of z, and for the r values for which this is giving the less than infinity, or this condition is satisfied, as giving the ROC, region of convergence. So without mentioning the region of convergence of the Z transform, it is not valid. Even we can say that what is the range for which this is converging, or what is the region of convergence, what is the value of this range of R which Z can take. So it defines the region of convergence. So Z transform is always defined with the ROC, as we do in the Laplace transform also. So the inverse Z transform, which is based on the Cauchy's integral x of n, you can get back this sequence x of n in 1D sequence using this x of z, which is known if that the case of the Z transform, and z power n minus 1 dz. So this integration is a contour integral which is in counterclockwise direction around the closed path in the complex plane. So this is one way to get this Z transform, and as generally defined in this way, and there are methods to find these inverse Z transform as well. So these are the Z transform pairs, we say. So we can get the x of Z from by using the summation, and then x of n from minus infinity to plus infinity if it is bilateral, or if it is a unilateral, that's from n is 0 to infinity. So the x of n can be obtained from x of Z as well. So if we take the examples, and through this example we can see the what is ROC and what does it mean, and also a few examples which are very common examples we will take for Z transform, and then we proceed with the transform which is for 2D and how we can interpret it, whether it is a unique transform or not. So we can find the Z transform of a causal signal. So x of n equal to a power n u of n for a is less than 1 here. So what is that? The signal a, it can be 0.5, 0.25 or any of the value which is a less than 1. So in that case that it is multiplied with u of n is a unit step sequence. So if you plot the sequence, that x of n in that case, where n is varying from 0 to infinity, and when n is less than 0, this u of n is 0. So a is, if you substitute a equal to some 0.5 or a less than 1, so in that case we can have n equal to 0, this gives this 0.5, and then a 0.5 square, 0.25 and so on. It's a decaying sequence. So this sequence x of n, for this, what is the Z transform of it? So x of Z we can say as that n is varying from minus infinity to plus infinity, substituting this x of n as n u of n, Z power minus n, that's taking the Z transform of it. So u of n exists only where n is greater than or equal to 0. So this summation is valid only for n is greater than or equal to 0. So we change this limits to n 0 to infinity, and a Z power minus 1. It's a very basic example of it. n. So what is the condition in which the summation can be formed in the closed form solution? So this a is Z power minus 1, so this needs to be less than 1. So that's the condition in which, so if it is less than 1, then we can x of C can be written as 1 by 1, this if this is considered to be x or a, any of this, so that's equal to 1 by 1 minus x. So this can be written in terms of the summation expansion also, and then find find that is going to be converging to 1 by 1 minus x, or 1 by 1 minus a Z power minus 1. So this would converge only when, what is the condition here is Z power minus 1 should be less than 1. So this parameter, that is a Z power minus 1, should be less than 1, so that we can get this closed form solution. For that other way, so from this condition we can get a by Z less than 1, so where Z is greater than a, the magnitudes. So if you simplify this, the transform a by Z and Z by Z minus a is the Z transform of this sequence a of n u n. So a is the value whatever it takes less than 1. So the condition Z greater than a implies the convergence, so that's the region of convergence here. So the region of convergence, let us look into it. So in the Z plane, so if you take this is the Z plane in which real of Z and the imaginary of Z can say, and where in the Z plane there is a unit circle, this a can be of less than 1 we said, so the unit circle will be somewhere above a. So if we consider this a is less than 1, and so we get the Z equal to a is this circle, okay, so here having the radius of a and the magnitude a, so that's going to be the circle, and the region of convergence is above this, the gray area, which is the shaded one, is the region of convergence for which this transform converges. So if it is less than a, it doesn't converge, actually, so that is less than a, it doesn't converge. So this is called the ROC of the a of n u of a. So a power n into u of n. So that's the sequence x of n in which this Z transform converges for the Z greater than a. So it's moreover, this is a causal sequence, that is it exists from n greater than or equal to 0. In that case, so the ROC is at greater than a. And So we got this Z. So we've defined this is the region of convergence for the right-sided sequence. So if we take an example of this anticausal signal, that is a signal which exists in the left side of the n in the axis. So if you plot the sequence, what we get, this has x of n is minus a power n of minus n minus 1. So we'll take a is again the less than 1 here. So if you plot this, because this is a negative sign, there is a negative sign here, so this would be the exponential decaying in this sense, and then in the negative way, where n is negative, and moreover this is multiplied with u of minus n minus 1. So this case is representing the sequences existing up to n equal to minus 1, from minus infinity to minus 1. So for this sequence, whether this Z transform exists, or what is the region of convergence for this sequence of this anticausal. Anticausal, what mean is here this n, it is n less than 0, the sequence exists. For that, if we take x of z, so the sequence exists between minus infinity to minus 1. So minus a z power minus n 1 per n, so that is x of n. Now the summation can be made it to making this m equal to minus n. So m equal to 1 to infinity, and this n is again we made is minus n equal to m. So my a power minus n z m. So because we have taken the minus n and make that as m. So minus n has made it as limit also to 1 to infinity. So this minus exists the outside the such, and then m is varying from 0 to infinity. We get is that m power m, and we make the same summation from 0 to infinity instead of 1 to infinity, so that this 0 component needs to be subtracted from the, because we need only the summation between 1 to infinity, and then so if we change it to 0 to infinity, and this is when m equal to 0, the whole thing becomes 1, that needs to be subtracted from this whole sum. So this is the case of here we have minus 1. So minus 1, this is converging to 1 by 1 minus a inverse z minus 1. So we know that this gives the closed form solution where a inverse z is less than 1. So that is going to be 1 by 1 minus a inverse z minus 1. So if we simplify this further, we can get the x of z as minus a inverse z 1 minus a inverse z. So minus term, so z by z minus a. So what is the region of convergence for this case? That is a inverse z is less than 1, so which result in z is less than a. So you can see the difference between the previous sequence and this sequence, in which this is z transform is same, z by z minus a, and there as well that's a right-sided sequence, and this is a left-sided sequence, this is an anticausal sequence. But region of convergence, there is a difference. This z is greater than a in that case. Here it is z less than a. So how do we get this? So we get a inverse z is less than 1, so that to get this form, and z is less than a. So if we plot the region of convergence for this this circle less than a, the radius, you have this shaded region gives the region of convergence, real of z and imaginary of z. So whereas in the previous case it was greater than a, z greater than a for that, and in this case it's less than a, but the z transforms are same, z by z minus a for two different sequences. So what we can conclude from these two examples is that the two different time signals may have identical z transforms. That means it is not the unique one for two different time domain signals, that is right-sided one in the first example, and in the second one left-sided sequence. Causal and anticausal sequences may have the identical z transform, and you see it doesn't correspond to a unique time signal. Okay, so unless this ROC is specified, so ROC needs to be specified with x of z, so that x of n can be taken, or the inverse z transform can give the unique time domain signal. So this is the mandate to specify the ROC when we give the z transform, and this is not unique for the time signal. So different time signals can have the same z transform. So with this, we can take the one more example, that one is the left-sided causal anti-causal sequence, left-sided sequence which was anti-causal, and then the right-sided sequence which is a causal sequence we had taken. So now we combine the both, like the one which we had taken, the first one a power n u of n, and the this is a power n u of n minus n minus 1. So this is existing as the right-sided causal sequence, and this is the left-sided sequence. So now if you plot them two, so you have the one here from 0 to infinity. So it's this is contributing to this sequence 0.9 power n, and whereas 1.2, this is going to be the next, this second sequence which is going up to -1 to this side minus infinity. Okay, so this is plus here, this is not minus. In the example we took that as a minus. So here is the sequence is which is both sided now. So what is the region of convergence, and what is the Z transform for this case? So if we take this sequence, and x of z is like z by z minus a, where a is 0.9. So as directly we can take it from the previous first example, and this one plus, which is z by z minus a, where it was minus in the second example. So we have taken the plus, so the sequence is only in the amplitude is positive. So is minus z, if you do the same process, minus z by z minus 1.2. So this sequence, a summation of this, and what is the region of convergence for this case? So the z needs the first one to converge. So in that case, here we had it z power minus 1 should be less than 1 in that case. So where a was 0.9. Okay, another case was a inverse z less than 1, where a was 1.2. So using these two things, like here 0.9 and 1.2, we get the region of convergence. In one case, z is greater than 0.9. Here z is greater than 0.9 and z is less than 1.2. So the combining the two cases, so z is between 0.9 to 1.2. So that's a, so we can combine for simplification as well. So if you take the common thing and then if you multiply and simplify it, it would get minus 0.3 into z. So the z transform we had obtained, and the region of convergence we specified as 0.9 to 1.2. In the z plane, if you visualize this real of z and imaginary of z, see the z greater than 0.9 represents this circle, and where there is a pole, and the other one is here 1.2. So the other pole, so which is greater than 0.9, the shaded region, and less than 1.2 is a shaded. This is an annular ring, like a case of in the z plane, which is the region of convergence for the sequence which is we have taken in for the discussion. Here is the two-sided sequence. In that case, this greater than 0.9 would go here as well in this region, whereas 1.2 would be in this regions, right? So less than 1.2 and greater than 0.9. So the ROC is the intersection of these two. So that's how we need to make that this ring is the region of convergence for this case. So greater than 0.9 and less than 1.2. So the intersection of these two would be the region of convergence for this sequence. So the common area for which, so if we have these two poles, then what is the region of convergence, which excludes these poles, actually, that in the first case also and in the second case also, when the ROC excludes the pole, and but it greater than 0.9 and less than 1.2. So in that case, that z is in between that 0.9 to 1.2 is the region of convergence for the two-sided sequence. Now if we take the example of this, or the inverse z transform in this case, but the one which we had already discussed were the z transform, obtaining the z transform for the three different cases. So that's very common examples, and from that we understand what is the region of convergence. So how do we extend this same thing if we visualize it in the 1D, the region of convergence, and how that can be extended to the 2D. So that we would look into it, and the inverse z transform, in which x of z is given as 8z minus 19, z minus 2 into z minus 3. So is this what is the valid or not? So what is the x of n for it? And if we give this transfer function x of z like that, so we need to specify that z. Otherwise, you cannot get this x of n for this particular Z transform. So, whenever there is an inverse Z transform problem, that we need to know that what is the ROC for which it was obtained. So, this ROC is Z greater than 3. Here it is given the ROC is greater than 3. For this, what is the x of n? So, that is the case of inverse Z transform. So, x of Z is, first if we are given with this partial fraction, so you can write this as a by z minus 2 and b by z minus 3. So, for which that how do we get this x of n from this inverse Z? So, you can use this table of Z transforms and see where a of n u of n is z by z minus a in the unilateral case. Then here we consider this unilateral case where n is greater than or equal to 0. Okay, so that's in that case, if x of n is equal to a power n minus 1 u of n minus 1, the u is existing from n equal to 1, not n equal to 0. So in that case, what is the transform? A power n minus 1 is that x of z is 1 by z minus a. So we can see the same case here as well, 3 by z minus 2 and 5 by z minus 3. So 3 into this case would be a power n minus 1 into u of n minus 1. So that's going to be 2 power, this is 2 here in this case, and 2 power n minus 1 this, and the 3 which is coming out to be the inverse in the as such in the inverse x of n inverse is Z transform, and 5 is taken as this plus, and 3 is going to be again here z minus 3. These two are in the same form where a of n minus 1, so which is equal to 3. So this a is the 3 power n minus 1. So u of n minus 1 is common. So these two sequences exist from n equal to 1, not n equal to 0. So these two are the right sided sequences. Summation of right sided sequences results in z greater than 3. So for this particular case, that z is greater than 2, so that it can converge, and for this case z is greater than 3, it is converge. So if we take the OC, that is the intersection of the two, which would be greater than 2 and greater than 3, so that would be z greater than 3. That's how we get this x of n here. That's a right sided sequence. So if the ROC is some other different between 2 and 3, so then this would be different, and that is depending on this sequence, what we get is depends on the ROC here. So the ROC is greater than 3, so this equation is valid now in the inverse Z transform. So this is unilateral because this u of n is having n minus 1 in the case of sequence. So if we take an example of another one in which that inverse Z transforms, where x of z is given something like that. So z is 2 z square minus 11 z plus 12 by z minus 1 z minus 2 the whole cube. So where all these Z transforms we use, these representations are used in the FIR and IIR filtered structures when we give the transfer function of this filter structure in 1D, and similarly the 2D Z transform also used in that case. So we represent that in the transfer function in the filter structures in this way. So the Z is generally, we say that this is one type of x of z in which ROC is specified as z greater than 2. So you can see depends on ROC, we need to take the inverse Z transform. So now, because we have this z can be taken this way, like here in the left hand side, and then we have the equation 2z square minus 11z plus 12, where z minus 1 to z minus 2 the whole cube. So we take this a by z minus 1 doing the partial fraction basically, and b by z minus 2 whole cube, and c by z minus 2 whole square, and d by z minus 2. So if we take, so this has the 3 poles, so 1 2 3 we need to take that, and this one is corresponding to z minus 1. So this has, so I think this is a simple method of partial fraction to take the inverse z. So find these residues using the residue method as well. So any of the methods can be used to get these residues. So by doing so, that we get this minus 3, minus 2 and 1 and 3. So for that we can have this, we have to take the inverse Z transform using the table. So now for x of z equal to z, so the one more step can be done here. This x of z equal to z by z minus 1, that minus 3 is there, plus z into minus 2 by z minus 2 the whole cube, plus z by z minus 2 the whole square plus 3 into z by z minus 2. So this term, so now if we take the inverse z for that, minus 3. So this is well known to us, that is a power n u of n. So in that case, this is also z is greater than 2. Okay, so u of n, so a of n u of n, a is 2. So we can, that is x z by z minus a, here is 1, the first case. And similarly for the last one also, 3 into z by z minus 2. So this pair of z transform helps in getting the inverse z for this case and this case, minus 3 and a is 1 here, 1 power n u of n. So minus 3 u of n, and this case is plus 3 2 power n. So that's the next last term. So but these two terms needs to be taken the inverse z. So for that x of n, suppose x of n is n into n minus 1 n minus 2 up to n minus m plus 1 by m factorial to a power m. So a power n into u of n. So this a power n into u of n is multiplied with the term which is having this in the unilateral transform, u of multiplied by u of n. So x of z would be z by z minus a, and it has the m number of, what is the m here, plus 1. So what we have is this form, z by z minus a, m plus 1 is 2 here and m plus 1 is 3 here. Okay, so using that we can get back the sequence, that is if m equal to, for this case it is 2, so in that case you will have n minus 1, if it is 2 minus 1 it will be 1. So that's how it is m factorial, that is 2 factorial, and then a is the 2 power 2 here. So what we get through this z transform pair, we can obtain the x of n as for this minus 3, that is simply a u of n, which is 1 power n into u of n. So we have taken it, these two terms, and 3 2 power n u of n, these two terms are okay. And for this minus 2 as such, n into n minus m minus 1, that is n minus 1, this becomes 2 power 2, so it is 8. So, and then 2 power n, which is here, also for this case x m equal to 1. So 2 power n as such, and n it is stopping with n, not n minus 1, n minus 2 and so on. So this is having the m factorial by 2. So here we have this n by 2, 2 power n, the minus signs. So these two are obtained through from the equation, the z transform pair here. So we can get the x of n, from which obtained sequence is this is unilateral, u of n is multiplied with the x of n, and this inverse transform is unilateral transform. So we can get the inverse z transform in this fashion. So you can go through this z transform table, which is for all the cases of all the signals, which is not part of this course, that we just want to introduce this 1D z transform, and we using this background of this z transform, that is the convergence, and it's a generalized version of the Fourier transform, z transform is. So using this background, we can apply or extend this z transform, 1D z transform, to the 2D z transform, and we will visualize this ROC, the region of convergence, where it is only a point in the z plane where is the real of z and imaginary of c. With respect to that, the region of convergence is defined in with the circle, or the pole existence of depends on the existence of the pole and pole magnitude. So that can be different in the case of 2D z transform. We'll see that how it is going to be a pole surface. It's not only a point in the one-dimensional case, as in the one-dimensional case, but it will be a pole surface. The region of convergence is different. We will visualize that in the 2D z transform. Also, this is not the unique, meaning that two different sequences can have the same z transform. So it is also valid in the case of 2D z transform. We'll see through the examples that, as we did in the 1D, that two different sequences, 1D sequences, have the same z transform unless until the ROC is specified. So similar case can be seen through in the 2D z transform as well. We'll see in the next lecture. Thank you.